All right, Gibson here. Today we're going to look at another phenomena of light, the changing of direction of light, right? We looked at reflection already, and now we're going to look at something called refraction of light. So the objectives for today are: how do we solve problems involving refraction? We'll do it both qualitatively, being able to predict whether the light will change direction, and then quantitatively, we can actually calculate how much it will change. And we're going to look at a particular case of refraction called total internal reflection. And what are some of the applications in the real world for that? All right, so let's talk about what the actual cause of refraction is. Why is it that light will change direction? Under what conditions does it change direction? So we're going to start with an analogy, right? Analogy is a model that's different, but helps us understand the behavior. So imagine you have a axle, right, with wheels at each end of it, and the wheels are glued tight to the axle. So the whole thing kind of has to turn together as it rolls. And we're going to roll this axle with wheels along the sidewalk and then up onto the grass. Now, you guys all know, right, from either riding your bikes or rolling a ball, that the speed is going to slow down when it hits the grass, right, the rougher material. So if we roll the axle there, as soon as it hits the grass, it slows down. Now, if we roll it perpendicular to the boundary between the sidewalk and the grass, right? So there's our normal line we've drawn, 90 degrees from that boundary. Then the direction remains the same. It does not turn. And the reason it does that is because both the left and the right wheel will slow down at the same rate. And so it'll continue to move in a straight line. Now, what happens if we do that at an angle? Now, you can tell as it approaches that boundary, the wheel on the left is going to hit the grass and begin to slow down first, while the wheel on the right is going to continue to travel faster. So let's see what will happen, right? When that hits, it tends to kind of drag the outer wheel around and change directions, right? It's because the inside wheel, the left wheel, is going to slow down first since it hits the grass first, okay? And we can see that it has an actual change in direction. And again, we're always going to measure that change in direction from the normal line, just like we did in a reflection off of a flat or plane mirror. So it turns out that waves, whether they're traveling through water, light waves, sound waves, or through air, they all bend when one part of each wave is made to travel slower or faster than another part. Okay, so let's see, how would this be applied to wave behavior? Well, we call that refraction. It's the change in direction of a wave as it crosses the boundary between two media in which the wave travels at different speeds. Okay, so the key words are here, it's between two media that have different speeds. Okay, if they have the same speed, no change in direction. So here's a little animation here that shows wave fronts. Okay, think of these as like kind of like water waves, right? Ocean waves coming in medium 1. And then when they hit medium 2, they slow down. And you can see a couple things happen. The direction of the wave front changes, but also the distance between the wave fronts change, right? The wavelength gets shorter because the frequency would be the same, but since the velocity drops, the wavelength will have to be shorter. So if we drew these lines to kind of represent the wave fronts, right, they're parallel to the wave fronts that are traveling, we would see the direction that those wave fronts are changing. We can also draw in a light ray, because we've done both models, right, of a wave and a ray, but typically we'll use a ray going forward here to model the change in direction. So we see that it actually would turn in towards the normal line. So here is an example from faster medium to the slower medium. Now, how do we tell conceptually which way the light ray is going to bend? something we call the pencil test. So the pencil test kind of serves like our wheel and axles, okay? So let's say we have a light ray that's traveling through the faster material at an angle, and it hits the slower ray. Which way is it going to bend? Is it going to bend towards our normal line, the dashed line in the middle, or further away from it? Well, here's where the pencil test comes in. You can literally, right, when you're looking at a picture of refraction, right, showing the light ray going from one material to the next, hold your pencil right up against the picture and move it down the direction of the light ray. But as you hit, in this case, the slower material, right, that end of the pencil is going to slow down, the other end's going to keep moving fast, and that helps you to understand which way it's going to change. In this case, the angle moves closer to the normal. We would have a smaller angle between the normal line and the light ray. How about from slower to faster? Well, same concept applies. Here's our incident ray. And if we use our pencil test, this time it's going to speed up first, right? And that's going to turn it away from the normal line. So when we go from slow to fast, we move away from the normal line. When we go from fast to slow, we move closer to the normal line. Now, let me just draw here and ask you which media is the faster media here. So here's the path that our ray takes, okay? So looking at its path and the angle between the normal line, right? We're going from, in material B, a large angle to the normal line, to in material B, a smaller angle to the normal line. So if we use our pencil test, right, we would see that it has to slow down, has to slow down as it hits material A first. That causes it to turn towards the normal line. So in this case, the material in A would be slower in the speed of light than in material B. All right, so let's apply a little math here, okay? Here's a picture of a light ray that's traveling from air into water. Now, you can observe this yourself, right? If you take a glass of water at home, fill it up, and just put a pencil into it, and then look at the alignment of the pencil in the air versus the alignment in the water, and it will look like it actually has a break in it, like it shifts over, okay? That's due to the refraction of light, the bending of the light as it does that. And so air to water is one of the more common cases where refraction of light occurs. So we have our incident ray. We call that the angle of incidence between the incoming light ray and the normal line. And we have our angle of refraction. That's the angle between the normal line in the other material and the refracted light ray. So we've already talked about this, right? In the wave, if the wave travels in a slower medium, the angle of refraction decreases. It moves towards the normal. And we can draw a picture of it doing the other direction, right? Going from slow to fast here, from water into air. And here we see that the angle of refraction is greater than the angle of incidence, okay? So it's going to move away from the normal line. So this one slide is probably a good one to get into your notes, right? It summarizes the two cases that we'll see, right? Speeding up or slowing down as it travels from one material to the other. All right, let's get into some math here so we can actually predict what those angles will be. And the first thing we have to understand is something called the index of refraction. And it's simply a ratio of the speed of light in a vacuum. Okay, so that's like the speed limit, right? 3 × 10⁸ meters per second. That's as fast as light will ever travel, as far as we know, in the universe, divided by the speed of light in a particular medium, something other than the vacuum of space. So think about this. The slower the medium, the larger the index is going to be, right? Because we're going to be, if it's traveling the exact same speed of light in a vacuum in the medium as well, we would have a ratio of 1, right? But as the number in the denominator gets smaller, right, the overall value of n, the ratio will get larger. So the index of refraction can never be less than 1. That would be the index for a vacuum, but it can certainly be greater than 1 if light is moving through slower material. So here are some common materials that we can measure the index for. And you can see what I just said. In a vacuum, light does not change speed, so it would be a ratio of 1. In air, we see a slight slowdown in the speed of light, so we see a number slightly greater than 1. But now the other materials, you can really see the difference, right? Water, 1.33, ethanol, think of that as alcohol, or one form of alcohol. 1.36, glass, like common window glass, 1.52, quartz, right? It's a natural occurring rock that has transparent qualities, 1.54. And look at the diamond. A diamond, right? A very hard material, one of the hardest materials found naturally on Earth, has an index of 2.41. The speed of light slows down dramatically when it travels through a diamond. So how do we use that index of refraction? We use it in something called Snell's law of refraction. And here's the math that allows us to calculate one of the angles if we know the other, or if we know both of the angles, we can calculate one of the index of refraction. Now, remember, n, small n, stands for the index of refraction. So in each material, we have, say in the top here, angle 1 and index 1. And then in the bottom material, we have angle 2 and index 2. And Snell's law of refraction basically tells us that the index times the angle in that material has to be equal to the index times the angle in the other material. Okay, so we're just setting this two factors that we multiply equal to each other from each side of our boundary here. So let's look at an example where we apply that, okay? So here, to use the law, right, we'll always have to know 3 of the 4 variables here. So here we're given the index for both materials, and we're given the angle, the incident angle, in what looks like to be probably glass, right, 1.52. So we're going from slow to fast here. That should result in the angle getting larger, but let's see what the math tells us. So we're going to start with Snell's equation, and we're going to put in the variables that were given and solve for the other, right? So what we're trying to do is solve for the sine of angle 1, really just angle 1, but initially we're going to get sine of angle 1 by itself. And so to do that, we're just going to divide both sides by n1. And then we can put in our values. So we put 1.52 for n2, 1.0 for n1, and then multiply that times the sine of 30 degrees. Okay, so we get this value here. The sine of angle 1 we're trying to solve for is equal to 0.76. Now, that's the sine of the angle. How do we find the actual angle? This is where we're going to use a little trig, right, to take the inverse, or sometimes called arc sine, of it. You'll find a key on your calculator or on your phone that says sine of -1. And so that's the inverse sine. And we take the inverse sine of 0.76, and then that gives us the actual angle. So if we do that, we see we get an angle here in this example of 49.6 degrees. So it makes sense. We expected to have a larger angle because we're going from slow to fast. Now, when you do these calculations on your calculator, make sure that you're in the degree mode, right? Often in your math class, you might have it in radians, but in physics, we will always use degrees, particularly with refraction problems. All right, let's try one more problem here. In this one, we know both of the angles and one of the index. We don't know n2. So again, we're going to use the same equation. This time we're solving for n2, right? So we're going to divide both sides by the sine of angle 2 and then put in our numbers. So I've already taken one step, right? N is equal to 1. The sine of angle 1 is 0.5. The sine of angle 2 is 0.34. And so in this case, we just do the rest of the math and we get an index of 1.46. Now, does that make sense? Remember, the index always has to be equal to or greater than 1. And that's what we got in this case. If you come up with an index on these problems less than 1, then you've made a mistake somewhere. And it makes sense, right? Because If you look at our light rays, again, we're going from slow to fast. The ray is moving away from the normal line. All right, so a couple applications here. You might have noticed this before, right? We normally have clear vision. Some of us need glasses or contacts to help us, but the principle in which a lens works is based on refraction. It actually is the slowing and changing of the direction of light as it travels through the lens. Because the lens is different material, slows down from the air in which the light rays are traveling to our eye. Now, in the normal light, or normal eye rather, the geometry is correct, right? It's going to focus that image on the back of our eye, called the retina, and everything works fine. Now, when you jump into a swimming pool and you look around underneath, you notice everything is blurry. Why is that? Why is everything blurry? Well, because our eyes and our lens has evolved to be just the right shape and thickness for having the light go from air through our lens to our retina. But if we go underwater, light is now traveling from water through our lens to our retina. And that's going to change the angle of refraction in the lens to where the focal point is actually behind our retina. And therefore, we get this fuzzy odd image that forms in our retina, and our brain just can't process it, right? It's not able to bring it into focus. All right, total internal reflection. Now, let's just do a little experiment here, right? We shine a flashlight, a beam of light from water to air. We know it's going to bend a little bit, right? Away from the angle or the normal line. Some of that light will be reflected. A small amount is always reflected back at the boundary, okay? Now, what happens if we keep making the angle greater and greater? So this is our incident angle compared to the normal line is becoming greater and greater. Notice what's happening to the refracted light. If we go steep enough, it's actually going to refract right along the surface of the water. It's going to bend so much that it's going to bend it right along the surface or the interface between those two material. We call that angle the critical angle, where refracted light travels along the surface. And then any angles beyond that, any larger angles, all of the light is going to get refracted back into the material. We call that total internal reflection. So it may look like the light's being reflected from that boundary, but it's really the principle of refraction that's causing it to kind of bounce off that boundary and back into the water. Now, what are some applications of this? You may have heard of fiber optic cables, right? These are very small glass fibers that light travels through, and they're used to transmit data. They can transmit data at extremely high rates, right? If you have internet service with fiber optic, you have some of the fastest internet service available. We don't have this in most homes right now, right? But some businesses will have fiber optic connections to the internet. So the light ray travels inside this fiber cable, this glass, and these are very small. You can see this bunch that is being held in the hand here. There could be 1,000 fiber cables in that bunch. And we can put the cables, the fiber cables, right next to each other without any casing or covering, because the light, as it travels through that cable, if there's a slight bend or anything in it, it's going to reflect or be captured back inside the glass fiber using this concept of total internal reflection. So this allows us to put a bundle of many, many, many glass fibers into one cable and be able to transmit literally thousands of data streams along those many glass fibers within the cable. And this really has been a huge technology that's enabled a lot of the communication systems that we have today. Another application, not quite so techy, is in diamonds, okay? Now, you guys probably don't have a diamond. Maybe someday you'll have a nice diamond in a ring. Perhaps you do have a real diamond. But when they cut a diamond, right, from the raw stone, they have to decide what angle they want to cut it, okay? And if they cut it too deep, the light will reflect and refract out the bottom of the diamond. You don't want that. It won't look very bright. It won't sparkle when the light hits it. If you cut it just right, and sometimes that's called the ideal cut, the light will actually refract and reflect back out parallel 180 degrees through the top of the diamond. And when it does that, that's when you get the sparkle. You get that most brilliant appearance of the diamond. And then too shallow, the same problem. We'll get light that will travel out the backside of the diamond. So diamond cutters understand this. They call it sometimes the ideal cut that will give you the most sparkle for a given diamond, no matter what the grade or quality of the diamond is. And one other application is that prisms, these are just triangles, three-dimensional triangles of light, actually make the best mirrors. Most mirrors only reflect about 90 to 95% of the incident light. Some of it gets absorbed or travels even through the back of the mirror. Prisms reflect 100% of light due to this total internal reflection, right? All the light comes back out. So if you look at some optical equipment, even telescopes and things, the very high quality equipment, rather than using a mirror, will actually use a prism to cause the light to reflect and change directions. All right, that's it. We've looked at how do we solve problems involving refraction. We know how to use Snell's law to actually calculate the angle, and we know that the index of refraction is the ratio of the speed of light in a vacuum divided by the speed of light in a slower material. And we can now explain total internal reflection. It's when the incident angle becomes large enough that all of the light is refracted back inside the material. All right, that's it. That's what I have for you today.